So in the video, we saw the guy on the pond, and he was using two styrofoam balls here and moving them up and down to mimic what's happening from the slits. So making two sources of waves that are in phase with each other. And then we saw they had a nice camera angle so that you could actually see the places where there was no wave and the places in between where the waves were bigger. So we get this this pattern of light and dark from the destructive and the constructive interference. So it was observed that you can shine light on a piece of metal and cause electrons to come off of the metal. This is called the photoelectric effect. And classic wave theory attributed this to the fact that the light energy was being transferred to the electron. If that were the case, then the theory predicts that only the amplitude or the intensity of the light would affect the emission of electrons. If you used brighter light, you should get more, and dimmer light, you should get less. But there must be some sort of a minimum threshold of light, and so we would expect that there'd be a lag time before the electrons were emitted. So you could use a dim light and you could still get electrons out, you just have to wait longer, because you'd have to wait for them to absorb the energy from the light. But that is actually not what happened. So this is a sort of a setup that we're looking at here. So here's a metal surface, light comes in, and electrons are emitted. So in order to measure the amount of electrons, you put this in an evacuated chamber, and you put a positive electrode over here by applying a voltage across this electrode in the metal surface, so that when the electron gets kicked off, it'll be attracted to the positive terminal. You can detect current flowing. We can actually measure that, yeah, there's electrons being emitted. So experimental observations gave this result. Here's the rate of electron ejection, and here's the frequency of the light. What they found was at low frequencies, you could shine that light on there all day long and no electrons would come out. There was no lag time. When you get to a particular frequency, all of a sudden, without any lag time, you get electrons being ejected. And you go to higher frequencies and you're still getting the same amount of electrons ejected. Intensity does have an effect. Higher intensity will get you more electrons, a higher rate of electrons, but intensity is not the only thing. At low frequencies, lower energy of the wave, it doesn't matter how intense the light was, it's not going to eject electrons. Any questions? This is suggesting that light acts as a particle. We've seen that light acts as a wave, but light can also act as a particle. So Einstein proposed that light energy is delivered to the atom in packets. Those packets, a packet of light is called a photon or a quantum. So a photon is a packet of light, a piece of light. The energy of that photon, that piece of light, is directly proportional to its frequency. Higher frequency, higher energy. We saw that earlier with the waves. So the energy of the photon is proportional to the frequency. Well, if it's proportional, there needs to be some sort of a proportionality constant, and that is called Planck's constant, and this is the value. You don't need to memorize that. I'll give it to you on an exam if you need it. 6.626 times 10 to the minus 34 joule seconds. You can also express that in terms of wavelength, because the frequency is equal to the speed of light divided by the wavelength of the light. So what this means is the reason that we saw this graph, let's look at the graph. So if light is a particle, at lower frequencies, those particles of light do not contain enough energy to eject an electron. Once you get up to this threshold frequency, this is the minimum energy needed to eject the electron. Then you will start getting electrons ejected. If you send in packets of light, photons that have higher energy, they will also eject electrons. So we can do calculations with this. A 100-watt light bulb radiates energy at a rate of 100 joules per second. A watt is a joule per second. Power is energy over time. If all the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? And they're telling us to assume 3 sig figs because these numbers were written kind of sloppy. Well, what can we do with this? Write down the numbers. Excellent. So I'm seeing 525 nanometers. That's the wavelength, right? 525 nanometers. And I'm seeing that I've got 100 joules per second. Okay. And what are they asking? They want photons per second. How many photons per second?
When you need one, they're all here.
What can we do with this?
1 joule per second.
Yeah, we have 1 joule per second, so this has something in common with this. If we could figure out how to convert joules to photons, we just looked at an equation that relates the energy of a photon to its wavelength or its frequency. So the energy of a photon equals Planck's constant times the speed of light over the wavelength. That would give us the energy of the photon. So Planck's constant, 6.626 times 10 to the minus 34 joules seconds. The units are weird, just write them down. 3.00 times 10 to the 8th meters per second. And then in the bottom, we're probably not going to want nanometers, are we? There's a meter up here. So let's pull that same trick and do 525 times 10 to the minus 9 meters. Well, let's look at what happens with our units here. So the meters cancel, and the seconds cancel, and I'm left with joules. Okay. So let's do the calculation. 6.626 times 10 to the minus 34 times 3 times 10 to the 8th divided by 525 times 10 to the minus 9. So I'm getting 3.7863 times 10 to the minus 19 joules.